In this lesson, we're going to talk about basic refrigeration systems, specifically the different types of systems that are available. We're going to begin with the basics, ice refrigeration. It's an ice chest. It consists of an insulated cabinet with a tray atop to hold ice. The food is located below the ice compartment, and the cold air flows downwards, cooling the food. It maintains a fairly high humidity level. Temperature ranges are between 40 and 50 degrees, in other words, medium to high temperature refrigeration. The ice chest, cold air falls down through the ice chest. The cold air falls down, and the warm air rises because it's less dense, hits the ice, and then falls down. Water will drip down into the condensate pan on the bottom or stay in the ice chest. Remember, warm air flows towards cold, and it will create a circulation pattern itself. This was the original ice refrigerator before mechanical refrigeration was invented. Next type of refrigeration, again, non-mechanical, it's called a desert bag. It's a wet bag or bag of water that has a little bit porous. In other words, lets a little bit of water through the bag. The moisture on the surface of the bag evaporates rapidly. Heat that causes the evaporation comes from the desert bag and its water. This heat removal cools the drinking water inside of it. Snow making is also evaporative refrigeration. Water flows from the nozzle. The air under high pressure breaks the water into tiny droplets. The surrounding temperature near or below freezing contains the water droplets to evaporate and rapidly cool. Ice is formed, and that's what builds the snow up. The next type was a flooded system. The pressure on the low side of the system will vary with temperature. For example, here we have a low side float control right in here. The evaporator level, or the level of the refrigerant, changes as the flow drops. The evaporator is empty. It allows refrigerant in through a needle, through a seating needle that's right there. As the evaporator fills up, gets closer to the suction line, we don't want to flood the compressor. We cut off the flow of refrigerant. There's also a motor control on the compressor. When the float is all the way up, the compressor actually shuts down until the float drops a little and more refrigerant is needed. External drives are called open refrigeration systems. The compressor is belt driven from an electric motor. The compressor has to have a crankshaft seal to avoid refrigerant flowing out or air getting in. These are primarily used on low pressure systems. The crankshaft seal in open drive systems is one of the most frequent places for leaks. And again, we have our motor, which is separate from the compressor. The seal that we're talking about is right around the crankshaft, and that is the biggest place for leaks. High side float systems are capillary tube refrigeration lines. Okay, they're frequently used with the high side float systems. Frequently specified in commercial applications where there's a very high operating efficiency. They're easy to service, but the charge must be very accurately. It's called a critically charged system. If it leaks, you empty it all the way out, fix the leak, and replace it with a weighed-in charge of refrigerant. This is an example of the high side float system. Again, as the high side rises in pressure, the float will shut off the flow of refrigerant from the compressor and the condenser. The motor of the compressor will shut off, waiting for additional refrigerant to flow out and through the system to the suction line. There's a thermal element on the suction line that senses when the refrigerant is flowing. Automatic expansion valves allow refrigerant to flow through an AEV when the compressor runs and reduces evaporator pressure. Pressures do not balance on the off cycle. The valve closes. The motor compressor must start under a load. They're very commonly used in small commercial appliances, and they have to be used with a temperature control. And again, AEVs, the automatic expansion valve is right there. There's a filter dryer before it, and the motor has to be controlled under a load. Thermally controlled expansion valves, or TEVs and TXVs, is controlled by the temperature of the TEV control bulb, the pressure in the evaporator, the spring pressure. Pressures again do not balance on off cycle, so the compressor very frequently starts under a load. It's used on large commercial refrigerators as well as in many air conditioning appliances. It can be controlled by pressure or temperature control. The TXV is a very high efficiency way of controlling refrigerant flow and is being used more and more in the high efficiency equipment. Your TXV is special because it's right there on the inlet of the evaporator, plus it has a sensing element that attaches to the suction line after the evaporator, and it controls superheat. The motor and the compressor must be controlled electronically, and 9 out of 10 times they have additional load requirements. The compression type system using the capillary tube is one of the most popular systems. They're cheap and easy to maintain. The capillary tube maintains a pressure difference while the compressor is operating. It has to be operated by temperature control. It will balance off the high and low side pressures during the off cycle since nothing shuts off. It's used in refrigerators, freezers, window air conditioners, and small dehumidifiers. They are not very frequently seen anymore in rooftop units or anything larger than 1 ton of refrigeration. The cap tube is actually an extension of the liquid line. Very small inner diameter, and the length and the diameter of the tube makes the difference. Multiple evaporator systems are one condenser connected to 2 or more evaporators, 2 temperature valve locations in the suction line of the warmer evaporators, the check valve located in the suction line of the colder evaporators. Sight glasses are often included in the liquid line, and a pressure motor control operates as a safety device. In other words, we want the system to go off on high pressure. It's commonly used in commercial refrigeration applications where you might have more than 1 cooling location. This is a multiple evaporator system. You have 1 evaporator there, you have 1 evaporator there. Both of them have TXVs, and you have a check valve in the colder one and a temperature valve or a solenoid in the suction line of the higher temp. Compound refrigerating systems consist of 2 or more compressors connected in series. Usually requires an oil separator for each compressor to increase system capacity during low temperatures. A single temperature motor control operates all the motors. A TEV controls liquid refrigerant into the evaporator. Pressures do not balance on the off cycle. The motors must start under load. They require heavy maintenance and frequent service. Again, 2 compressors. There's number 1 and number 2. They are piped in series. 1 flow of refrigerant through both compressors. Cascade systems differ a little bit. It's 2 refrigeration systems connected in series. Both systems operate at the same time. Each system has a TV and 1 motor control is used. The motors must be capable of starting under load since the pressures do not balance. A condenser evaporator is usually a shell and tube flooded evaporator type. Refrigerant must be very dry because water will condense or freeze. It's used in industrial process where objects must be cooled below -50 degrees. 1 condenser gives up heat to another one's evaporator. In other words, it's a stepstone. Here's a cascade system. Compressor A, which is down in this area here, cools through the evaporator, cools condenser B. Then condenser B has that extra cold refrigerant that it's starting with and further cools whatever the substance is we're trying to cool using compressor B. Modulating refrigeration matches machine capacity to heat load. It uses 2 or more compressors connected in parallel. Each compressor is operated by a pressure type motor control, and they use most often TEVs or TXVs. Same evaporator is connected to all compressors. Pressure controls are in the suction line, which is common. This is an example of a modulating parallel refrigeration system with 3 compressors, 1 condenser, and 1 evaporator. They must have a liquid receiver so that there's always a clear flow of liquid to the thermostatic expansion valve on the evaporator. Ice makers The motor and compressor is usually, and condenser is usually located in the bottom of the cabinet, or they might be water cooled. The accumulator, the ice cube mold, and the electric defrost are all in the upper part over the bin. Most surfaces are in contact with water, and ice are stainless steel. This is a food making equipment and must be treated as such. They require extra care, extra cleaning, and they must think about it. People are eating this stuff. Drinking water coolers uses a hermetic airtight compression refrigerating system, uses a cap tube. The water pressure regulates and adjusts the water flow. Condensing unit is air cooled, and the condenser fan increases capacity. The thermostat maintains the desired water temperature of approximately 50 degrees. So again, this is a tube and tube evaporator. Condenser is air cooled. The water inlet comes in, wraps around the drain pipe for heat exchange, and then runs along the evaporator so that there's a heat exchange between the two tubes. Some of them might actually have an extra chilled water tank down here. Expandable refrigeration system, it's called chemical refrigeration or open refrigeration system. It's used on trucks and other vehicles to transport or store frozen foods. It consists of heavily insulated spaces cooled by liquid nitrogen. The system discards the refrigerant after it has evaporated. It's excellent for shipping frozen foods since it maintains about -20 degrees. And again, we have a tank of high pressure nitrogen, liquid nitrogen with a little bit of gas at the top. That feeds through, gets colder as the pressure drops, and it sprays into the space and cools as it boils off. There's a temperature sensing element that turns a valve on and off on the liquid side. Thermoelectric refrigeration transfers energy from one place to another using electrons rather than refrigerants. A thermoelectric couple moves heat from the inside of an insulated space to a heat exchanger. Electrons carry the heat. The fins on the evaporator increase heat flow. Fins on the heat exchanger give off heat to the surrounding air. There's no moving parts. The thermal efficiency is very low. And this is an example of a thermoelectric refrigerator. Notice, no moving parts. Very good for like an automotive, boat, recreational, and small office cooling. Semiconductors of two types. The N-type conduct electricity by flow of negatively charged particles, that's electrons. P-type conduct the electricity of flow of positively charged particles called holes or electron holes. Several NP pair junctions are connected in series to produce significant cooling. It's used in electronic equipment as well, like computers and aerospace devices. More of these are connected in series, and it increases cooling. You have a hot surface or cooling surface and a heat sink. It's the flow of electrons between the N and the P that create the cooling. A thermostat controls the rectifier, which controls the AC power. Dry ice refrigeration is almost the same as ice cubes or ice refrigeration. Dry ice is a solid carbon dioxide. The dry ice changes from solid directly to vapor through sublimation. The dry ice is packed beside or on top of food. The carbon dioxide, as it changes to a vapor, is a latent heat change, and that absorbs heat, changes from solid to vapor, and keeps the food frozen. Now, just a quick safety note. Never handle dry ice with your bare hands. It will cause instant freezer burns. Always wear heavy gloves. This is an example of dry ice refrigeration. You have slabs of dry ice and the food. You don't have to have drains, but you must have air vents or the frozen food cabinet will explode. Intermittent absorption system uses a generator charged with water and ammonia. The heat source is a kerosene flame, heats the solution in a generator. Piping is welded steel due to high pressures on the generating cycle. Intermittent absorption systems are popular in areas where electric power is not available. It will run off a generator. This is an absorption system. Notice the kerosene burner at the bottom. The ammonia and water is heated and separates. The ammonia vapor goes into the evaporator or the air-cooled condenser, takes heat out. It will condense back into a liquid. It will go into the evaporator, boil off, absorbing heat, and return to the heating, the generator, or the area where the heat is. Do not breathe ammonia in, it's dangerous. Continuous cycle absorption system is operated by a limited amount of heat furnished by gas, electricity, or kerosene. There's no moving parts. Operation is based on Dalton's law. Consists of four main parts: a boiler, a condenser, an evaporator, and an absorber. Unit charge consists of quantity of ammonia, water, and hydrogen. It's widely used in domestic refrigerators and recreational vehicles. Example of a continuous cycle absorption system is right here. Same applies. We take and heat the ammonia in the boiler. Off the top of the ammonia, we have ammonia vapor. It comes into the condenser, changes to a liquid form, goes into the evaporator, boils off, comes down into a strong ammonia solution in the absorber, and returns and does the cycle all over again. Solid absorbent refrigerant is principles based on experiment done by Michael Frady. This is an example of solid absorbent refrigerant. We have, again, silver chloride and ammonia. The condenser is warm, and then you heat it up, and it will cool the water. The evaporator is cold. Sophisticated systems are various conditions, and refrigeration requirements require some additional add-on devices. Accessory devices can make systems safer and more efficient. For example, note the pressure regulator, the vibration damper, crankcase heaters, filter dryers, suction service valves, crankcase heaters, oil separators, liquid desuperheater, and defrost control. Hot gas defrost during refrigeration cycle is a timing mechanism that directs hot, high-pressure vapor from your discharge side of your compressor through the evaporator to remove frost and ice. Solenoid valve number 1 is open during normal refrigeration system, allows the refrigerant to come through the complete cycle. During hot gas defrost, the system goes into the right-hand mode, which the solenoid number 1 is closed, and the hot gas valve opens. The hot gas valve is right here. It allows discharge gas to bypass the condenser, bypass the meter device, go directly into the evaporator, and it melts the ice off. During this defrost cycle, solenoid number 1 on the liquid line closes. No liquid refrigerant is flowing through the TV into the evaporator. Solenoid number 2 is open. Hot compressed refrigerant vapor flows through it directly into the evaporator. As the hot water vapor passes through the evaporator, it melts the ice from the evaporator surface. Electric defrost can be used as well. The system shuts down. Notice the electric heating elements alongside the evaporator. Right there. The system will shut down and melt the ice off the evaporator. The refrigerant unit is not running and there is no flow. Resistance heating elements are now shown in red because they're hot, and it's designed again to melt the ice off the evaporator. Ice is an insulator. It will continue to build up on an evaporator that's running below 32 degrees. Again, let's talk a little bit about safety. Wear goggles and gloves at all times, especially when charging and discharging refrigerant. R717, which is ammonia, is irritating to the eyes and lungs. You want to avoid exposure to it. Dry ice will cause instant freeze burns. Never handle it with bare hands.